So one type of structure, remember, that we tend to focus on at the beginning of your education is beams. They're relatively simple, and a lot of stuff that you might be looking at can be modeled as a beam. Like, the wing of an airplane. Obviously, it's got its aerodynamics effects, but from a structural standpoint, it is a beam fixed to the fuselage that has, like any other cantilever beam, that has a distributed load over it. So again, in general, beams are structural members designed to be holding various loads that are applied along its length. Got point loads, you got distributed loads, and combinations thereof. So generally speaking, the way we're going to be designing them is we figure out what sort of shear forces, bending moments, axial loads, so on and so forth, are produced by the loads we're planning on putting on this thing, and then we figure out what sort of cross-section and what sort of material we need in order to properly hold those loads. So we're often going to classify them based upon what's holding it up, based upon its supports. So again, if we have only 3 unknowns, then we can typically solve for it using just the equilibrium equations. So, like this simply supported beam, this overhanging beam, a cantilever beam, those are all types that can be found out based upon just the equations you already know. Other stuff, there may be other types that have more unknowns and at least techniques to solve for at this point. So like a continuous beam here, where it's got, it supports on either end and something in the middle too. A cantilever beam that has a support at the end, a fixed beam that's fixed between 2 walls. That's, we can figure out what's going on there, just not using only the equilibrium equations. We need to use more advanced techniques in order to determine what the reactions would be, and thus the loading situation. So when we're trying to find the bending moment at any point, or the shear load at any point, or the axial load at any point, or whatever it is we're trying to find, we do is we have a look at this thing and we determine the reactions at the supports, but just by treating the beam itself as a free body, like we've been doing this entire time in this course. You take the beam, you cut it at the point of interest, and then you draw your free body diagrams for the cuts. So again, one thing, so I believe I mentioned in the last video that our sign convention is somewhat arbitrary, but we need to be consistent. So essentially, if you'll see this situation here, we've got a reaction load, we've got these 2 loads down here, and then we've got an overall, we've got a shear force that's resisting that. So it's essentially, the way that's based upon the sign convention that I'm going to we're going to be using in this course, and in 331 if I have you again next semester, next year as well, is that essentially if the shear load at a little slice would cause it to rotate clockwise, then that is a positive shear load. So essentially, if we zoom in on a little slice here, zoom in on that, and if the load got a shear load here, shear load like that, then we'd call that a positive shear load. Whereas if we instead have a load that would be causing counterclockwise rotation. Oh, wait. Like that, then we call that a negative shear moment. Shear load. And then we also have the concept of the sign convention for a moment. So essentially, what we're going to be doing there, that's based upon the curvature. So essentially, when there is a bending moment, we call it a bending moment because it causes the beam to bend. So the degree to which it causes that, of course, depends upon how stiff the beam is, what the load is, etc., etc. But if you have some sort of bending moment that would, if you started out flat and it causes a bending like this, so it's a concave, so essentially if it forms what we call like a smiley face, then that smiley is positive, essentially. If you'd be able to say hold water there, then that's going to be positive. If you have a moment if you have a load that is instead causing curvature like that, that's a frowny face. That's a negative moment. And we'll talk about kind of why we pick those conventions in a second. They might seem a bit less than intuitive, but it is what it is. So yeah, essentially we take the cuts, we solve for the moments at that cut that would cause it to remain in equilibrium. Now, just keeping in mind, when you take your cuts, again, this is somewhat arbitrary. The fact of the matter is that at this point, we expect what we call the internal load to be the same, right? It's a consistent measurement from the internal load. But if we look at this face, that's got a clockwise moment. If you look at this face, it's got a counterclockwise moment. Got this face, the shear force is pushing that face down, whereas we look at this opposite face, it's pushing up. So there's not really any one correct answer for kind of which is which. So we just got to pick something and kind of go with it. So to plot the shear and bending moment, and oh yeah, the one point I'd like to make, when you're plotting it, this is almost always x. Along the length of the beam is going to be x, unless you got a really good reason to not do that. If it's a 3D problem, or if you're dealing with a structure that has beam like this, a beam like this, and you're connecting them together, then you're going to want to be consistent about your signs. Sorry, your coordinate systems there. But anyways, if you don't have a good reason, then x is along the length of the beam. So yeah, essentially, we'd start off by solving for the reactions. Obviously, in this situation, the reactions at the supports is going to be P over 2. And then, to the left of P, the shear load's going to be constant, and the magnitude of that is going to be the same as the reaction there. And that's just based upon our equilibrium conditions. It's going to be if we're pushing up on this end, in order to maintain equilibrium, we need to be pushing down on this end, so on and so forth. And then the moment needs to vary as a function of the position, because you've got a constant force, but as you're moving out and out and out, and you take those slices, the force couple that V and RA here form increases because you've got the offset that's even further. So the moment increases as you get away from the support. And then you get to a point where you apply this load P, and then suddenly, if we just take the, I already have it drawn here. If we take the free body diagram, we've got this load's going to change suddenly because we need to take into account both this and this. So based upon that, to the right of P, the shear load is going to drop down. It's going to drop down to P over half. So it's going to go from negative P over half. So it's going to drop down from a positive P over half down to a negative P over half. So the amount that it drops is going to be the same as the amount of the load. If we have multiple loads, that works the same way. As you kind of cross them, going from left to right, the diagram jumps up and down based upon whether or not the load that you're applying is pointing up or down. And then again, once we get past that point, the moment still varies as a function of position, but we're taking into account both this force and this force. And this one's bigger. P is bigger than P over half. Well, obviously, P is bigger than P over half. So the effect of the P load is going to be more than the effect of the P over half load. So it's going to, where it was increasing, now it's going to start dropping. And again, it's going to drop kind of at the same rate there. So when you have a beam with only concentrated loads, between those loading points, the shear is constant, and the moment varies linearly. Varies linearly. And the slope of that line is equal. The slope of your moment line is going to be equal to the magnitude of your shear. So essentially, what you're doing is you're integrating this from here to here, and that gives you that change there. So we'll do an example. So we're going to start out first off by solving the equilibrium equation. So let's go ahead and let's take a moment. Sum of the moment about B. So start going from left to right. 0 is equal to, got a 20 kilonewton force times 2.5 meters. So again, that's counterclockwise, so that's positive. And then we have the 40 kilonewton force and 3 meters. Again, from relative to B, that'll be a clockwise rotation. So that'll be negative. And then we're going to have this reaction force at D here, so that'll be a positive moment. And that'll be 5 meters times dy. So let's see, that gives us dy is going to be equal to, let's see, it's 40 times 3, that's 120 kilonewton meters. We'll move it over positive when we move over to the other side, minus the 20 times 2.5. So 20 times 2.5 is 50 kilonewtons. And, 5 meters dy is that? So dy is going to be equal to 70 kilonewton meters divided by 5 meters. You scroll down a bit so you can see my writing. So that's going to be, what's that end up being? It's 14 kilonewtons. Okay, so we've got that, and we can use that to solve for reaction at B. Now let's just go ahead and solve for the X reaction at B. Force in the X is equal to 0, which is equal to Bx. Hey, there we go. Shocking that that came up. So the next thing that we should go ahead and solve for is the Y reaction at B. So we got the forces in the Y direction is equal to 0. So B's presumably going to be a positive reaction. So let's go ahead and let's see here. We got negative 20 kilonewtons minus 40 kilonewtons plus 14 kilonewtons plus By is equal to 0. So moving those other ones to the other side of the equation gives us that's 60 minus 14 so that'll be 50 minus 4 is 46. By is equal to 46 kilonewtons. Okay, so I'm just going to redraw our free body diagram for this structure. I'm going to try to do a better job of redrawing our free body diagram for this structure. There we go. Okay, so 20 kilonewtons, 40 kilonewtons, 46 kilonewtons, and 14 kilonewtons. Okay, so we'll just go straight into this. So let's draw our shear diagram. Okay, so our shear diagram as a function of x. So we've got this load here. Again, when we're going from left to right, adding a force upwards caused it to have a positive internal load. So here we're doing the opposite. So we are going to be starting out with a negative 20. We're going to be starting out with a negative 20. That's going to continue for the 2.5 meters it takes to get to point B. And then we are going to jump up. So this upward force applied there increases the shear. So up 20. Another 20, and 6, close enough. And then we are staying constant there for another 3 meters until we hit point C here, and then we are jumping down. So I'm going to label these minus 20, 26. So at 26, 26 minus 40 That jumps us back down, and that'll be minus 14, and it stays at minus 14 until we hit the reaction there. And then that reaction jumps us up 14, which conveniently gets us back to 0, which is exactly where we expected to be. So that is our shear body diagram, or our shear force diagram. Some people like to label the negative ones just to make it crystal clear which is which. So now that we've got that, we can go ahead and draw our moment diagram. So our moment, again, as a function of x. So two things we know. At a free endpoint, or at a pinned connection, it is the internal moment is going to be 0. That's because there's nothing there. There's no external moment applied that will be causing the generation of internal moment. The internal moment is generally generated by offset with a shear. So if we have that, if we haven't had a chance to pass through any shear, then we haven't generated any moment. So it's going to be 0 at pinned connections, at a fixed connection, a fixed support, or where there's an actual external moment load applied, then we could have 0 at endpoints. But oftentimes you'll be starting off at 0. You'll be starting off at 0, and then you're continuing. And you're continuing here with a slope of minus 20. And that slope of minus 20 continues, with a slope of minus 20 kilonewton meters per meter, basically. Because for each meter we move here, we get an increase in the moment of decrease in the moment of 20 kilonewton meters. So again, this point is 2.5 meters out. So we can just draw I'm going to draw the moment diagram in orange. So that's let's call that a slope of 20. So we're going to hit this point here. So that point there, the magnitude of the difference between here and here is going to be the area of this section here. So starting at 0 and going down 20 times 2.5, the moment at that point is going to be negative 50 kilonewton meters. And then we reach this reaction point here, so all of a sudden we started off at negative shear, now we're in positive shear. So the moment starts increasing, and it does so at a slightly faster rate. So we're starting off at minus 50, and now it's shooting up at 26 kilonewton meters per meter. So it's the difference between here and whatever point we have here is the area here. So that's a 3 meter section. So 3 meters times 26 means that'll be 78. So we go from the minus 50 to and add 78 to that, so that'll be 28. So let's call that right about there. Its magnitude isn't quite as high as here, although the slope's a bit higher. And then once we hit this point, we start dropping down. So we start dropping down at the slope's going to be the smallest of the magnitudes of these. So we start dropping down with a slope of 14 kilonewton meters per meter, and that 14 kilonewton meters per meter exists for 2 meters. So that means that the difference between here and the end point is going to be 14 times 2, which is 28, which we had 28 here, which means that we're dropping down to 0, which is, hey, exactly what we expected to happen. We knew we wanted to get to 0 at the endpoints, and we did. So that's a good sign that nothing got screwed up in the process. If you do your diagram and you end up at the end, and it's a pin connection at that end or a free connection at that end, and your moment is 0, that is a big sign to you that you screwed up and you got some problems to fix. So again, some people might like to draw a little negative sign here to indicate that this is a negative moment. We may also be asking you to kind of sketch the way that this thing kind of flexes as it goes. So here you kind of start with your original shape, and keeping in mind where the kind of points are that you're stuck, you're going to get a certain amount of flexing, and you know that this portion here, it's going to be kind of like it's going to be forming a shape like that, whereas for this section here, the curve's going to be this way. So we know, based upon that, and knowing kind of that our fixed points are here and here, we can kind of expect that this thing might be doing something like that. Again, these sketches are expected to be kind of rough, but as long as the inflection point, where you're kind of switching over from a slope that is decreasing to as you move right to a slope that's increasing as you move right, needs to be at this point, then you're good to go. One other thing that you may have noticed is that you have your local maxima and minima on your moment diagram at the point where the shear force diagram crosses the 0 axis. Especially if it's an abrupt switch. If it's an abrupt switch because of a point load going from here to here, then you're gonna get a corner at that point. But we'll talk about what happens with non-abrupt switches shortly. The only other thing that you might need to keep in mind is that we also have a normal force diagram. So normal force as a function of x. Let's try drawing a better straight line. There we go. Close enough. So if that is our x-axis, and this is our normal force as a function of x, for this particular loading condition, here is our diagram. Let's assume that both of these are straight lines. The axial force in this case remains 0 throughout the entire beam. Okay, And yeah, that's it for now.